Hey guys, we are looking at circular motion. This is our last set of notes for this unit. I didn't have a chance to record it today and forgot to bring my camera home with me, so you guys are just getting the PowerPoint itself. Sorry you don't get to see my happy smiling face this evening, or, well, in this case when you're watching this tomorrow, today. Anyway, yeah, so circular motion. This is getting into, again, obviously, like the two words that are combined together here, circular motion. It's things that are in motion in a revolution or rotational motion, which is actually the first thing that we're looking at. What's the difference between a rotation and a revolution? Any object that is turning does so about an imaginary straight line called the axis. So the way that it is turning around, or the way we would say it's turning about the axis, causes some kind of change. If the axis is located within the body, so if the axis goes through the body, we call that rotation. If the axis is located outside of the body, that motion is called a revolution. So I've got an example here. This disc is rotating about its axis because that axis goes through the disc that's rotating. So you'd say that disc is rotating. But this ladybug that's sitting on the outside of the disc, it is turning around in a circle, but it is revolving about the axis because, again, that line of that axis of rotation is not going through that ladybug. So that's why we call that a revolution instead of a rotation. Tangential speed. So it is a linear speed. We know that linear speed, we calculate the distance, or we calculate it using distance per unit of time, right? That's just our regular formula for speed, distance divided by time. If an object is traveling around in a circular path, the distance that it travels, if it goes around one full rotation, or one full revolution in this case, the distance that it travels in that one rotation is equal to the circumference of the circle, which we should all remember from at least geometry, if not before that. Circumference of a circle is 2 times pi times the radius, where r is the radius of that circle. So if we can replace that distance in my formula with that, that'll be the first part of our formula here for tangential speed. And then there is a difference between the lowercase t here in my formula and this capital T that we'll be using. Capital T represents what we call the period. So it is the length of time it takes for that object to do one full rotation. So one full revolution, one full turn is called a period. So how long it takes to do one full rotation is capital T. So if we replace those two things with 2 pi r, our distance is 2 pi r in one full turn. Our capital T is our period, is our time that it takes to do one full rotation. That is the formula that we can use to find the tangential speed of that thing that is rotating. And that's going to be the linear speed of that object along that circular path, which is easy to visualize if we take a look at this next picture. So I know Michael talked about this in the Vsauce video you guys watched yesterday. Well, today, but yesterday for you. Where linear speed, we call it tangential speed because this ball that's rotating, if we're imagining something being swung around in a circle, it would fly off in a linear direction, right? That path is not going to curve. And it flies off in what we call tangent to the circular path. Now, in geometry, we used tangent to mean two different things. Right? We talked about tangent of in terms of trigonometry, right? The tangent of a right triangle. But we also talked about a tangent line to a circle, where a tangent means that it intersects my circle at exactly one spot. And it's always going to be perpendicular to the radius at that point. So in this case, it would fly off tangent to that circular path in the direction that it was currently traveling. So that's why we call it tangential speed. It is a linear speed. We are going in one direction. It's just going to continue going in that same path. So that's why we can go back and forth between those two things. Rotational speed is a little bit different than tangential speed or linear speed. Rotational speed, or angular speed as sometimes it's called, is just the number of rotations that you do per unit of time. So instead of looking at the distance that you're traveling over time, it's looking at rotations over a unit of time. Most commonly, we'll use RPMs rotations or revolutions per minute is our most common unit for that. We use the Greek letter omega, which looks kind of like just an extra curly W to represent rotational speed. So then we could say, again, just how many, like in this case, 30 RPMs means that that object is rotating 30 times per minute. Looking at two objects here, if the red ball and the blue ball are both on this same spinning disc, the same rotating platform, since they're doing the same number of rotations over that same time period, they have an equal rotational speed. However, the object that's further away, the blue object in this case, the blue ball, has a greater tangential speed because its radius is bigger. It's further from that center of rotation. It's going to have the bigger tangential speed because of how we calculate tangential speed. An alternative way of calculating tangential speed and rotational speed are related using this formula where V, here's my velocity, that's my rotational, or my tangential speed. I can also calculate that by taking the radius times the number of rotations per minute. So instead of calculating your tangential speed using 2 pi r over my capital T, I can also use this formula as well. So obviously in this case, the greater the the faster the platform spins, the greater the tangential speed will be, which makes sense. Again, we go faster, it's going to fly off faster. But we also can increase the tangential speed by increasing the distance from the center. The radial distance increases, that tangential speed is also going to increase. All right, a little question to test ourselves here. On a merry-go-round, the horses along the outer rail are located 3 times farther from the axis of rotation than the horses along the inner rail. If a boy sitting on one of the inner horses has a rotational speed of 4 RPM and a tangential speed of 2 meters per second, what will be the tangential speed and rotational speed of his sister sitting on one of the outer horses? So here we have to analyze kind of both of those. My rotational speed would not change because, again, they're on the same merry-go-round. Even though the outer horses are further away, they're still doing one full rotation in the same exact time limit. So that 4 RPM is going to be the same for the outer horses and as it is for the inner horses. Now the tangential speed is the one that differs. Because we are 3 times further away, it is going to have a 3 times greater tangential speed. So if the tangential speed of the inner horses is 2 meters per second, the tangential speed of the outer horses would be 6 meters per second. So, centripetal force. In order for an object to move along a circular path, there has to be something acting on it in order to change its direction. Right, as we're spinning this ball on a string in a circle, it is constantly changing directions. Right, as it wants to, its momentum wants it to continue on its path until it's acted on by that outside force. Right, we talked about that last unit. So here we are constantly changing directions, which means we have to have a constant force acting on our object in order to hold it in its circular path. That force that's acting on it in order to change its direction is called the centripetal force. Centripetal means center seeking. So that force is going towards that axis of rotation, that center of your circle, and it is pulling the ball towards that direction so that it's always changing its direction to stay along that circular path. There's a lot of different places where that centripetal force can come from. It could be tension on the rope that we see here. It could be a normal force pushing up against something that's, holding it on circular path. It could be gravity. There's tons of different types of forces that can act as the centripetal force, but when there is circular motion happening that's holding an object along a circular path, we call that a centripetal force. So in this example here, we're looking at a car that is driving around a curve. A sideways acting friction between the tires of the car and the road keep the car moving safely along its circular path. So in this case, it is friction that is holding that car at in its kind of curved path, along its circular path. It's not necessarily gravity. There's no string holding onto the car that's pulling it around the curve. It's that friction between the car's tires and the road that's allowing it to stay along that path. Now, the door pushes against you. If we're going around a curve, the door exerts an inward normal force on the passenger. You are a different object than the car itself. There is that force pushing against you that's keeping you along your circular path. Or in this case, in this picture here, we can see the driver does not have a door to the right of him or her. So it would be the seatbelt that's holding it in / friction of, butt on the seat that's making it go towards the left. Now, I know, again, Michael talked about this in the video we watched yesterday, but when we go around a curve, we feel like we're being pulled outward, but it's because we're trying to continue moving forward, and the car door is pushing against us to move us back along that circular path. So it's not like there's an actual force pulling us directly outwards. It's because we always have that force pulling on us or pushing against us, in this case, directly to our left, that makes it feel like we're being thrown outwards. So it's a center-seeking force. That force is pulling us in, even though we feel like we're being pulled out. If a road is slick or the friction's not great enough, the car is not going to be able to make that turn. It's going to have a tendency of skidding off the track at tangents to the curve. And you can see here, this is kind of a nice demonstration of this. You can see where the Formula One cars lose their traction if they don't have enough friction to keep them along this path. When they lose control, they fly off not at curved directions, curved paths, but you can see when they lose control, they go straight off here, tangent to the curve that they would be taking otherwise, which is kind of cool. Another thing that, again, I talked about this already, but another type of centripetal force is gravity. So the gravitational force on the moon, on satellites, on a ton of different things, all can be a source of centripetal force, and that's what's causing that rotation, that revolution of the moon around Earth. So that's what's keeping us along its circular path. This is also something that washing machines take advantage of, that centripetal force. It exerts an inward force on the clothes as it spins around it. Again, the drum of the washing machine is providing a normal force against the clothes that are in it. As it spins, it pushes the clothes back into it. And then the holes that are in the wash tub, drum, whatever you want to call it, has holes in it, and that as it starts to spin around, those little spots where there's no normal force pushing it back against the water or some other small thing, if there's little dust particles or dirt particles and stuff, they're all going to fly off in tangential paths along the outside the drum wall, which is kind of cool. Centripetal force, we have this thing. We're probably not going to go into a whole lot of depth of this today. We'll do a little bit of it with our lab that we cover. We're going to try and minimize this as much as possible. We talked about tension being the source of a centripetal force. It doesn't always necessarily have to be perfectly perpendicular. We do have these situations where a conical pendulum, meaning that you're kind of spinning it here and making a cone, which is why we call it conical, right? We got the circular path here. The tension, the string that we're holding it at, does not go directly to that center of rotation in the middle of our circle. It's up above, outside of our circle, and it kind of still follows along that path. So there's only two forces acting on what we call the bob, the weight, the ball. There is gravity that's pulling it down, and then tension pulling it up towards that anchor point up at the top. We can figure out the centripetal force here. Now, in both of these, I guess neither of these, should I say, are the centripetal force. Tension is one thing that's acting on the object. Gravity is the other thing that's acting on the object. But neither of those numbers, if I calculated what the tension is on the string or the gravity that is pulling down on my bob, are my centripetal force. I would actually have to do some vector calculations to find that horizontal component vector that is center seeking towards the center of my circle. So this T of X, this tension just horizontally, would be the actual calculation that I have to do to be able to find what that centripetal force is. Since the bob doesn't accelerate vertically at all, the net force in the vertical direction is going to have to be 0. So that's how we would be able to figure out what that is. We would be able to weigh our mass of, or find our mass of this bob, because we know that the vertical forces have to be balanced. So then if we know what the tension is on the string, we know that vertical aspect, we can calculate what that horizontal aspect is as well. So then T of X is the net force that's on the bob, which is the centripetal force. Another way, we talked about this already with the Formula One cars and not always necessarily having enough friction to make super steep, or I guess super sharp curves. One thing that they can do to reduce that high-speed skidding is by what they call banking the turns. So they actually take this and they take the road and elevate it on one side. This is called super elevation, where the inward part is lower than the outward part. So the outside part is banked up higher than the inside one is. And they do this because there is, besides the friction of the tires on the road, or the racetrack, whatever it is, that does not usually happen on regular roads, but along with that, we have the normal force that's always pushing up against our cars. Right? Anything that's sitting on a surface, that's sitting on your counter right now, that's sitting on your desk right now, there's a normal force pushing up against it. Your butt that's on the seat is pushing back up against you to keep you from falling through it. That is also something that if we have our normal force not acting perfectly vertical, we have a little bit of component vector horizontally that can add to that friction in order to increase that centripetal force, in order to keep you on a circular path that might be more extreme than just what the circular path would be if it was just a flat curve. So if we had a vehicle that had no tendency to slide down the curve or up the curve, at that speed, friction would play no role in the vehicle on the track. So again, if it doesn't curve up, if it doesn't curve down, it's not sliding left or right, then friction is not acting on it. The only two forces that are acting on that vehicle would be weight pulling down and the normal force pushing up against it. So again, here, just like with that conical motion, we have that normal force that's acting at an angle from where our center of the circle is. So since gravity and the normal force for the vertical component, those two have to be balanced. That inward seeking, that horizontal component of my normal force would be the centripetal force, which is what this next statement is saying. I'm not going to restate that. All right. As we talked about before, so there is no such thing as centrifugal force. It is centripetal. Centripetal is the actual name of it. That's that center seeking force. Centrifugal force doesn't happen with the circular paths that we're talking about. A centrifuge is something that can be used kind of like what your washing machine does, where it spins really, really fast to try and separate things, or it causes a rotation, a pulling motion. But a centrifuge is different than a centrifugal force. Centripetal force is that force that's pulling it along its circular path. There is nothing like this that's going to happen. We already talked about how if the string were to break, it's not going to peel off and curve outward or go directly out, perpendicular to my radius. That's not going to happen. It's going to follow in a tangential path in order to continue along its momentum. We've kind of talked about this already. Again, centripetal force is not a new kind of force, or it's not like gravity or tension or normal force or air resistance or any of those other ones that we've talked about, applied push or pull. It's not any new form of force. It's just the force. Any kind of force can be a centripetal force. It's anything that is acting on an object that is keeping along its circular path. So it could be gravity, it could be friction, it could be tension, it could be normal force, and electrical force, gravity. Any of those things could be a combination of them, like we talked about with that car banking. It could be friction on the tires and normal force because the road is banked. Could be anything. All right, getting into another calculation here. Centripetal acceleration. So since our body is undergoing a uniform circular motion, that means there is a constantly changing velocity, a constantly changing speed, because we are constantly changing the direction. And we have to be able to find the acceleration of this body. So this is our formula for centripetal acceleration. It is velocity squared over my radius. So my acceleration, I have a sub c here just for acceleration of the centripetal force. So centripetal acceleration is equal to v squared over my radius, velocity squared over radius. Since we have a centripetal acceleration, we also know the mass of an object is constant. We also can calculate using Newton's second law the centripetal force that is applied to our object, which is going to be super useful. We've been talking about centripetal force. We can actually measure it using centripetal acceleration. So if we know the mass of our object that's rotating or revolving, and we know how fast it's rotating or revolving, we'll be able to figure out that centripetal, that tangential speed. Therefore, we will figure out what the centripetal acceleration is, and then the centripetal force, which is nice. Again, these forces are always causing a circular motion, and that acceleration results in the fact that it's always going to be directed inward for that centripetal force. We've talked about this already. Although the speed of an object is undergoing uniform circular motion, the speed is constant. The body is accelerating because it's constantly changing direction. We know that velocity and acceleration vectors are always perpendicular to each other. It's accelerating inward in order to stay along that path. The velocity is continuing tangent to that circular path. All right, so suppose we have a ladybug that is placed in the bottom of a can that is being whirled around in a circle. So you put something in a can, it's some string attached to it, you're spinning it around in a circle. That string is pulling on the can, pulling it inward towards the center of that rotation, and so then the bottom of the can is also pulling inward on that ladybug. Now, when you're doing that, as you spin it around in a circle, that same spinning motion can be used to generate a simulated gravity. If you were the ladybug in the middle of this can and it was spinning around in a circle, if it was spinning at the right speed, if you were spinning it fast enough or at the correct one, not too fast, you could spin it in a way that it simulates gravity. The ladybug would still feel like it's just sitting there in the can without it being spun. This is how you can simulate gravity. This is how artificial gravity works. This is actually what they do on the International Space Station. If you have it spin at the correct speed, you feel like you're in, instead of being in free fall, you feel like you're in the same gravity. Now, how you do that takes a lot of calculations, and you have to have the correct rotational speed in order for this to be the case. Because in order to do this, you need to rotate that body, depending on what size it is, at a speed that correctly resembles Earth's acceleration. Right? We know that the acceleration due to gravity on Earth is 9.81 meters per second squared. So you have to rotate that body in a way so that wherever you're going to be standing, wherever you want gravity to be simulated, you have to accelerate it in a way that acceleration that you feel is 9.8 meters per second squared, which is kind of cool. So again, space stations, the way that these would work, if you wanted to try and simulate gravity, one cool example is not Interstellar, Passengers. The one with Chris Pratt and Jennifer Lawrence, where they're like going through space and then they wake up too early and stuff, and all that other stuff. But you can actually see that the way that spaceship moves through Earth, moves through the universe, it's rotating as it's going through its path, and that is how it's accelerating, like how it's creating gravity. You can also see this in 2001: A Space Odyssey, kind of one of the famous early sci-fi scenes is where this guy is running on a track, but it's this, like, he's running vertically up and down on this rotating space station. And in order for us to simulate the gravity, you've got kind of two different options. You could have a relatively small radius of that space station, in which case you're going to have to spin pretty quickly in order to kind of simulate that 9.81 meters per second squared for that acceleration. Or if you had a big space station, if you had something that has a much larger radius, you could have a slower rotation because, again, you've got that distance that since it's 9.81 meters per second squared, if you have a larger distance that's going to be covered, you can have a smaller speed that's going to be covered. All right, last question here. How would one's weight be affected if the Earth were to begin spinning faster on its axis? So here, this is very similar to a question that Michael talked about in the spinning video you guys watched yesterday, where he talked about traveling east versus traveling west. If you were able to weigh yourself as you were doing that, there was a slight difference in your weight in those two directions because you're either traveling with Earth's rotation or against Earth's rotation. Here, I think for most of us at this point, it's pretty easy to see that if the Earth were to begin spinning faster, that acceleration that we're experiencing, that tangential speed would be greater, so therefore we would weigh less if we began spinning faster. That is all I got for you guys for today. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you guys soon.